Okay, so we got a question about cyclic groups, which I'm going to answer in this video. Before I do that, I thought it would be nice to just talk a little bit about groups in general. So maybe like, why are they important? Why are you studying them? So the answer is that groups arise in any situation where symmetry is involved. As an example, I want to look at the symmetries of a regular hexagon. So first, for a regular hexagon, we have some rotational symmetries. And here I've kind of drawn some pictures to illustrate them. So starting with this picture of a hexagon where I've numbered the vertices 1 through 6. One thing that we can do is we can rotate this hexagon 60 degrees counterclockwise. If we do that, then we're going to end up with the same shape. Although the vertices have shifted position, so basically everything shifts over one unit counterclockwise. So 1 shifts up to the top, 2 shifts down to here, and 3 shifts down, and so forth, okay? So when you rotate by 60 degrees counterclockwise, you get the same shape of a hexagon, but the vertices have moved over by 1. Now we can also rotate an additional 60 degrees for a total of 120 degrees counterclockwise. So if we start with the original numbered hexagon, rotating counterclockwise by 120 degrees, that will shift all of the vertices over by 2 in the counterclockwise direction. But otherwise, you get the same hexagon shape, all right? So you can continue doing this. You can rotate by an additional 60 degrees for a total of 180. So all the vertices are going to shift over by 3 counterclockwise. You can rotate an additional 60 for a total of 240. So all the vertices will shift over by 4 this time, okay? Again, you can rotate by an additional 60 for a total of 300 degrees. So in this case, each vertice moves over by 5 places. And finally, if you rotate an additional 60 degrees for a total of 360 degrees, what happens here is every vertex is just going to move back to its original position. So this last rotation, rotating by 360 degrees, it's the same as just rotating by 0 degrees or just doing nothing, in the sense that none of the vertices or none of the points move around. So it's literally just doing nothing, okay? All right. Now I've labeled these rotations. So the first rotation by 60 degrees counterclockwise, I'm calling it R1, and I'm also calling it R. This rotation, rotating by 120 degrees counterclockwise, I've called it R2. But of course, there is a relation between R2 and R. So namely, rotation by 120 degrees counterclockwise is the same as rotating by 60 degrees twice, all right? So here I'm kind of using a sort of multiplication notation to represent rotating by 60 degrees once and then twice. So this is really, this multiplication is really function composition. But I'll denote it as multiplication. So we have this relation that R2 would be equal to R squared. Similarly, rotating 180 degrees counterclockwise. So it's the same as rotating 60 degrees 3 times. So you can say it's equal to r cubed. Rotating 240 degrees counterclockwise is the same as rotating 60 degrees counterclockwise 4 times altogether. So r to the 4th power, and so on and so forth. Here at the end, what happens is if you rotate by 60 degrees counterclockwise 6 times, so r to the 6th power, it's the same as doing nothing. And I'm denoting this symmetry of doing nothing as E. So this E here, just doing nothing, it represents an identity element. Okay? So for instance, if I do nothing and then rotate by 60 degrees counterclockwise, well, that's the same as just rotating 60 degrees counterclockwise. Likewise, if I rotate 60 degrees counterclockwise and then do nothing, the ultimate effect is also to just rotate 60 degrees counterclockwise. So like r times e and e times r are both equal to r. So e is behaving like an identity, okay? All right. Now, so we know that for groups, every element should have an inverse. So we know, for instance, since r to the 6th power gives you the identity, you can say, for instance, r times r to the 5th power would be the identity, meaning that r and r to the 5th are inverses of each other. All right, so in other words, if you rotate 300 degrees counterclockwise, that's r to the 5th power, then you can undo that and get back to the original hexagon if you rotate by an additional 60 degrees, okay? And so because of that, that makes these two guys inverses of each other. Likewise, r squared and r to the 4th are inverses, because if you rotate by 240 degrees followed by 120 degrees, that's a total of 360, so it's the same as doing nothing. And likewise, r cubed is its own inverse, because if you rotate by 180 degrees twice, that's the same as rotating 360 degrees total, which again is effectively doing nothing. Okay, so rotating by 180 degrees will undo itself. It's its own inverse. Okay. So here, looking at this symmetries of a regular hexagon, we see the structure of a group appears. Okay, you can sort of multiply these rotational symmetries together. The multiplication being function composition or applying one after the other. We have the identity element, which is just rotating by 0 degrees or just doing nothing. And then we see that each of these rotations, each of these symmetries has an inverse. Now, in addition to that, there are also some reflectional symmetries of the regular hexagon as well. And again, I've drawn some pictures illustrating them. So one thing we could do is we could reflect the hexagon about this vertical axis. So I've numbered the vertices once again, and if you reflect about the vertical axis, what happens is the 1 and the 3 would swap places, and the 4 and the 6 would also swap places, okay? So one thing that I want to note right now is If we were to apply this reflection again, so apply it twice, so what would happen is first 1 and 3 will swap places, but then if we reflect again, they're going to swap again, which will bring us back to the original orientation. Likewise, 4 and 6 would swap, but then if we reflect again, they would swap again back to their original places. Okay, so that shows us that S squared, applying this reflection twice, will give us the identity symmetry. So the symmetry of just doing nothing. So that shows us that this reflection is its own inverse. And that's the same for all of these other reflections as well. If you reflect twice, it's the same as doing nothing. So every reflection happens to be its own inverse. And then we can also reflect about this axis, and then this axis, this horizontal one, this one. And we can reflect about this axis, and then continuing the pattern, the next axis I would draw would have been the vertical one, but that was the first case, so that would be all of the reflectional symmetries, okay? All right, now something else I want to notice is if we try multiplying some of the rotations and reflections together, what happens? So let's observe something looking at these hexagons that I have here on the right. So notice that this hexagon, it's the same as this hexagon up here, except all the vertices were shifted over by 1 counterclockwise. So 3 is now up top, 2 has shifted down to here, 1 has shifted down, and so forth. Okay. So in other words, to get from this hexagon to this one, we can accomplish that with a simple rotation by 60 degrees counterclockwise. So this reflection S2 about this axis, it's equivalent to reflecting about the vertical axis first, so applying the symmetry S, followed with the rotation by 60 degrees counterclockwise. So S2 we could say then is equal to R times S, because this reflection can be accomplished by applying this reflection and then a rotation after that. Likewise, these two hexagons are also related by a simple counterclockwise rotation by 60 degrees. So again, notice that all of these vertices just need to shift over by 1 in the counterclockwise direction in order to get this hexagon underneath. Okay? All right, so that tells us that this reflection S3 about this axis can be obtained by reflecting about this vertical axis, and then after that, rotating 60 degrees counterclockwise twice. So applying R twice or applying R squared, okay? So this pattern kind of continues. Maybe I'll just illustrate one more. Okay. So to obtain this hexagon from this one, you just need to apply a counterclockwise rotation by 60 degrees. Okay. So shift all these vertices counterclockwise by 1, and you're going to get this hexagon. Okay. In other words, then, the reflection S4 about this horizontal axis is the same as first reflecting about the vertical axis up here. So applying S first. And then afterwards, if we rotate 60 degrees counterclockwise a total of 3 times, we'll get to this hexagon here. So S4, you could say, is equal to R cubed times S, okay? So you can kind of look at the rest of the pictures and you'll see that the same idea will persist. All right, but again, what I'm trying to emphasize with all of this is how these symmetries have a group structure to them. So there is a binary operation, function composition, or applying one symmetry after the other. And function composition, this binary operation, it is associative. And then we've talked about how there is an identity symmetry, which is the symmetry of doing nothing. And we've talked about how all these symmetries have inverses, okay? You can play around a bit. I won't spend too much more time on this, but for instance, try multiplying 2 reflections together and maybe see what that will do for you. You should find that multiplying any 2 reflections will actually give you a rotation, okay? So if you want to mess around, that's something you can explore on your own. Okay. All right, but as I said, the symmetries of a regular hexagon, they form a group, okay? So if I list all the symmetries that we talked about, the rotational symmetries, followed by the reflectional symmetries, all of them form a group with the binary operation of just applying one after the other, or function composition. Now, we saw how we could express all of the rotations and all of the reflections as products involving R, counterclockwise rotation by 60 degrees, and S, which was the reflection about the vertical axis. Okay. So because every element of this group can be expressed using just R and S, we see that G is generated by the elements R and S, okay? Now, if we just focus on the rotational symmetries only, so they would form a subgroup of this larger group of rotational and reflectional symmetries. Okay? So it satisfies the 3 conditions that a subgroup needs to satisfy. So it is closed under the group operation, multiplying any 2 rotations or applying any 2 rotations together will just give you another rotation. It has the identity element, rotation by 0 degrees. And we talked about how R and R to the 5th are inverses and so forth. So it is closed under inverses. Now in this case, every element of this group can be expressed using just the element R by itself. So we say that H is generated by the element R, okay? So H is an example of what we call a cyclic group. A cyclic group is any group which is generated by a single element. All right, so I'm going to talk a little bit more about cyclic groups now. So in general, cyclic groups can be finite or infinite. It's a cyclic group of order n. So that's just a cyclic group with n elements in it. So it will look something like this. You'd have the identity element in it, of course. You'd have a single element A, which generates the whole group. So that all the other elements would be powers of A, up to a power of A to the n minus 1. And if it's a cyclic group of order n, then A to the n will give you the identity. So the next power of A will just bring you back to the beginning, and then subsequent powers of A will just sort of cycle through what we have listed in here, okay? Now you can also have an infinite cyclic group. So in such a case, if A was the generator of G, and if G was infinite cyclic, then it would just consist of all possible or all integer powers of A, okay? So a couple of things to note about that is when n is 0, we consider A to the 0 to be the identity element, okay? And then as for the negative integers, those are for, because we need to have inverses in a group. So A to the negative n would be representing the inverse of A to the n, okay? Now, we have this notation for cyclic groups. So we write it as G equals, and then we have these sort of triangular brackets, I guess, and A. So this notation is just saying that G is cyclic and generated by A, okay? All right. Now, because cyclic groups are generated by a single element, their structure happens to be quite simple. And we have what I think your textbook calls the fundamental theorem of cyclic groups. So this theorem basically, you can say it tells us everything that we need to know about cyclic groups, everything that we could possibly know about cyclic groups, okay? So I guess cyclic groups are so simple, we have like a sort of a complete description of them is what's going on, okay? So here I've listed some of the facts that are talked about in this fundamental theorem of cyclic groups. So one fact is that all subgroups of a cyclic group are also cyclic. Okay, so that's the first fact that I have stated up here. And then I have some specific facts about if we have a finite cyclic group of order n. So let's say G is generated by A and it's of order n. So first is that A to the m will generate G if and only if m and n are relatively prime, meaning the greatest common divisor is 1. If D divides n, that's what this notation stands for. If D divides n, then A to the D will generate a unique cyclic subgroup of order n over D, okay? And there are no other subgroups of G aside from the ones that we've mentioned over here in the second item, okay? Okay, so you maybe don't fully understand what I just said and all of that. So let me try to illustrate by looking at the example that we saw earlier, the rotational symmetries of a regular hexagon. Okay. Okay. All right, so as I noted earlier, H is a cyclic group generated by the element R, and it is cyclic of order 6 because there are 6 elements in this group, okay? All right. So let me let me consider first this element at the end, r to the fifth. So I want to talk about this guy first. What I'm going to do right now is I'm going to just start computing powers of r to the fifth, okay? All right. So r to the fifth squared. Okay, so that would just be r to the 10th power. All right, but we know that r to the 6th gives us an identity, right? So if we look at r to the 10th, that's like r to the 6th times r to the 4th power. And since r to the 6th is just the identity, identity times anything will just give you, the thing that is being multiplied. So e times r to the 4th is just r to the 4th, right? Okay, so let me see. So we started with r to the 5th, and then when we squared it, when we raised it to the power of 2, we got r to the 4th, okay? Okay, so next let's consider if I did r to the 5th power but cubed. So that would be the same as r to a power of 15, which I could imagine is r to the 6th times r to the 6th, and then times r cubed. Okay. And each of these are identity, so multiplying it all out will just leave you with r cubed. Okay. All right, so I'm going to compute r to the 5th and now raise to a power of 4. Okay, so that would just be r to a power of 20, which of course we could say is 20 is 6 plus 6 plus 6 plus 2. And each of these are an identity, so when we multiply all this out, we'll just be left with r squared. Okay. Can maybe see the pattern, but if I now take r to the 5th and raise it to the 5th power, okay, so it's r to the 25th power, and 25 is 24 or 4 sixes, and then plus 1, so times an extra r to the 1. And since each of these are an identity, when we multiply it all out, it's just equal to r. And then if we do r to the 5th power, but then to the 6th, so that's r to the power of 30, which I guess you can think of as being r to the 6th, but multiplied with itself 5 times. And since r to the 6th is just an identity, that means we just get an identity in the end, okay? So what I want to notice then is when we consider the group generated by r to the 5th, so considering all the powers of r to the 5th, well, it actually gives us the entire group H, right? We got every single element of H just by taking powers of r to the 5th power. So H happens to be generated by r, but it also happens to be generated by r to the 5th, okay? Because considering all powers of r or all powers of r to the 5th will give you every single element in the group H. Okay. So that's what this first item and the fundamental theorem over here is talking about. 5 and 6 are relatively prime. They have no common divisor aside from 1. So because 5 and 6 are relatively prime, that is why r to the 5th power generates the entire group H. Okay? Let's look at the second item. So if D is a divisor of n, okay, so n in this example is 6. So 2 happens to be a divisor of 6. Let's consider r squared. Okay. So if I consider what are all of the powers of r squared? Okay. So of course we have r squared, and then r squared squared will give us r to the 4th power. R squared cubed will give us r to a power of 6, which is an identity. Okay. So when you consider powers of r squared, you just get e r squared and r to the 4th, and that's it. So considering powers of r squared, that does not give you the entire group H. So r squared does not generate H. So what happens is instead it generates a subgroup of H. Okay. So if D divides N, then A to the D generates a cyclic subgroup, okay, of order N over D. So notice that this cyclic group is of order 3, which is N over D, 6 over 2. Okay. Likewise, 3 is a divisor of N. So if we consider the cyclic subgroup generated by R cubed, well, so considering powers of R cubed, so we have R cubed, and then R cubed squared is an identity. And then after that, it'll just kind of cycle back and forth between E and R cubed. Okay. So again, R cubed does not generate the entire group, because we do not get all the elements of H just by considering powers of R cubed. So instead, R cubed generates a cyclic subgroup of H, and the order of this cyclic subgroup happens to be 2, because there's only 2 elements in it. So in other words, the order is N over D, 6 over 3, okay? That's what the second item is talking about. Now, it's maybe of interest to maybe think about what about r to the 4th power? Excuse me. If we consider powers of r to the 4th, okay, so first starting with r to the 4th, r to the 4th squared is r to the 8th power, which is the same as r squared. And then r to the 4th power but cubed gives us r to a power of 12, which is just going to be the identity. So r to the 4th also does not generate the entire group. It does not generate the entire group because 4 is not relatively prime to 6. Okay? Now, in fact, notice that r to the fourth generates the same cyclic subgroup as r squared. Okay. That's actually because 2 and 4 have the same GCD with 6 of 2. So it turns out powers of the generator that share the same greatest common divisor with the order will generate the same cyclic subgroup. And so that kind of shows you sort of the uniqueness of each of these cyclic subgroups. Okay. And then there are no other subgroups aside from these cyclic subgroups here, okay? So maybe just to draw a little picture of what we call a subgroup diagram for this cyclic group of order 6. All right, so we have the group H, and then we have a cyclic subgroup of H of order 3. So that was the cyclic subgroup generated by r squared, which has 3 elements in it. Then we had a cyclic subgroup of order 2. So that was the cyclic subgroup generated by r cubed. R cubed generated a cyclic subgroup of order 2. And then, of course, we have the trivial subgroup consisting only of the identity element. And the identity is a subgroup of every group, so it's a subgroup of this group as well as a subgroup of this group over here. Okay. So this is what a subgroup diagram looks like. You might be drawing a few of these in this class. So roughly the way you want to do it is you want to order your subgroups from like largest to smallest. So the largest ones or the bigger ones are going to be further up in the diagram. The smaller ones will be further down on the diagram. And you draw lines connecting two subgroups if one is a subgroup of the other. So like here, E was a subgroup of both this group and this group. Each of these guys were subgroups of H. Okay. All right, this subgroup is not a subgroup of this one, though. So I don't want to draw a line from here to here then, because this guy is not a subgroup of this guy. Now, E is a subgroup of H, but I don't draw a line connecting it because it's already sort of connected via this path altogether, okay? All right, so that's just sort of a small example of a subgroup diagram. And a small example illustrating these statements about a finite cyclic subgroup, okay? Another one of the statements in the fundamental theorem is how a cyclic subgroup of order n will be isomorphic to the integers with, what do you call this operation? Addition modulo n, I guess is what you would call it, right? And so I'll do an example involving that if you're not too familiar with it, so I don't want to talk about it at the moment. Now, if G is an infinite cyclic group, then A and A inverse will be the only generators of G. Every non-identity element will generate an infinite cyclic subgroup. and there will be no other subgroups of G aside from these infinite cyclic subgroups, and of course the trivial subgroup consisting only of the identity element. Okay. Also, every infinite cyclic group is isomorphic to the integers with addition. All right. Now, I want to focus more on the finite cyclic group, so let me just do one more example. So I think the example that I was asked to do was an example of the group Z36 with the operation being addition modulo 36. Okay, so first, what is this group? So the group Z36, it consists of the numbers starting at 0, 1, 2, etc., going all the way up to 35. And then what happens is the next number, 36, we sort of identify or equate 36 as being the same as 0. So then, like, if 36 is 0, 37 would become 1, 38 would become 2, and so forth. So if you will, you could say like 36 is equal to 0 modulo 36. You might see this kind of notation sometimes. You might also see notation like 36 is equal to 0 modulo 36, and so forth, okay? All right, but that's the idea of this group. And the group operation is addition. But for instance, if you do like 4 plus 35, okay. So 4 plus 35 is 39, but we would say that 39 is equal to 3 because we're doing addition modulo 36. So really 4 plus 35 in this group would be equal to 3 rather than 39, okay? So that's how this group and the group operation work. So 0 is the identity element still. 0 plus any other number will just give you that number. And every number has an inverse. So for instance, 3 plus 33 gives us 36, which we're saying is the same as 0. So in other words, 3 and 33 would be inverses of each other in this group, okay? All right. So there are 36 elements altogether from 0 to 35. So this guy is it's a group of order 36, and it's also cyclic. Yeah. And it's cyclic because it is generated by the number 1, okay? So remember, the group operation here is addition. So if you take the number 1 and keep adding it to itself, 1 plus 1 is 2. 1 plus 1 plus 1 gives you 3, and so forth. So considering all sums of 1 will generate all the elements of this group. So hence 1 is a generator for this group. And since it is generated by a single element, that is what makes it cyclic. Okay, now, first, let's ask the question, what other numbers are going to generate Z36? So according to the statement that I just sort of highlighted there, if you will, all right, so here, so maybe I'll just make maybe one note first before I answer that question. So up top, I was using multiplicative notation for the group operation. But here we are using addition instead. So instead of talking about raising 1 to a power, so when I was talking about like r to the n earlier, this was really saying apply the operation n times to r. But if the group operation is addition, then it's not that I'm multiplying 1 with itself n times, but I'm really adding 1 to itself n times instead. And of course, that looks confusing. So when you're using addition to notate the group operation, rather than talking about raising something to a power, as you can see, it makes more sense to talk about multiplying by that integer instead. So r to the n is what you would use for your notation if you are dealing with a group operation, which you're denoting with multiplication. But if you have addition as your group operation, if you are denoting your group operation as addition, then you want to be talking about multiples of elements as opposed to powers of elements, okay? So the other generators of this group Z36, they would be the multiples of generator 1, where m and n, 36, are relatively prime. So the greatest common divisor would be 1. And of course, m times 1 is just m. So basically, we're saying the other generators will be the numbers which are relatively prime to 36. Okay? So thinking about all the numbers between 1 and 36, which of them are relatively prime to 36? Well, to figure that out, it's probably useful to list out all of the divisors of 36. So let me think. The divisors 1, 2, 3, 4, not 5, but 6, 9, 12, let's see here, 18, and then 36. Okay. Okay, so the numbers which are relatively prime to 36, oh gosh, well, let's see here. 1, of course, 5, because 5 is prime. 7, 8, 9, 10, 11, 12, 13. Because none of the even integers would work. 15. 15 doesn't work because 15 shares the divisor of 3 with 36. 16, 17, 18, 19, 21. Okay, so 25, its divisors are basically 1, 5 in itself. None of those are divisors of 36. So 25 and 36 are relatively prime. 29, 31, 35 factors as 5 times 7, so it has no common divisors with 36. Okay, so unless I missed one, those are all the numbers which are relatively prime to 36. So those would be all the generators of Z36. And then what are all of these subgroups of Z36? So according to this theorem, the subgroups are going to be cyclic subgroups generated by A to the D, where A is your generator and D divides N. But since I'm using addition as my group operation, then rather considering powers of a generator, I want to consider multiples instead. So the subgroups will be generated by M times the generator 1, but this time where M is a divisor of N. So the subgroups will be cyclic. They'll be generated by multiples of 1, where M divides N. And they will be of order N over D. That's the other statement in the fundamental theorem over here. So order N over D. And then these will be the only other subgroups of Z36. All right. So I listed all the divisors of 36 already over here. So each of these guys will generate a cyclic subgroup. So as we know already, 1 generates the entire group. Okay. 2, so the group operation is addition. So the cyclic subgroup generated by 2 would just be all sums or all multiples of 2 then. And then 36 is 0. Okay. So it generates this cyclic subgroup. And notice the order is 36 over 2, or 18. Of course, I guess here the order was 36 over 1, which was 36. All right, so then the cyclic subgroup generated by 3, the next divisor in our list over here. So that would just consist of all the multiples of 3, because it's 3, 3 plus 3, 3 plus 3 plus 3, and so forth. You'd go up to 33, and then 36 becomes 0. Okay. So how many elements are in this group? The order would be 36 over 3. So there's 12 elements in the group. The next divisor that we had was 4. So the cyclic subgroup generated by 4 is 0, 4, 4 plus 4, 4 plus 4 plus 4. So all the multiples of 4 up to 32, and then 36 becomes 0. There will be 36 over 4 or 9 elements in this group altogether. The next divisor was 6. So 6 generates the cyclic subgroup consisting of all multiples of 6. Up to 30, and then 36 becomes 0. The order of this cyclic subgroup is n over d, so 36 over 6. And then we have 9, 12, 18, and 36. Okay. So let's do 9, 12, 18, and 36. All right, so again, 9 generates the cyclic subgroup consisting of all the multiples of 9. So 0, 9, 9 plus 9, so forth. 36 is 0, so we'd stop at 27. So there are 4 elements in this group, which you could have figured out by doing 36 over 9. The cyclic subgroup generated by 12 consists of 0, 12, 12 plus 12. 12 plus 12 plus 12 becomes 36, which is 0. So as you see, the order is equal to 3. 18 generates the cyclic subgroup consisting of 0, 18, and then 18 plus 18, which is 36, which is 0. So it's a cyclic subgroup of order 2. And then remember 36 is 0. So it's the trivial subgroup consisting only of the identity element, and it's of order 1. Okay. So these are all of the subgroups of Z36. And then maybe just to finish off this video, just maybe for practice, let's consider the subgroup diagram for Z36 then, okay? All right, so remember, try to order it with the larger subgroups on top and the smaller ones progressively further down. So, of course, Z36 is, of course, the largest subgroup of Z36, so we start with that. So the next largest subgroup was this subgroup generated by 2 of order 18. We have this subgroup of order 12 generated by 3. It's smaller, so I want it a little bit further down in my diagram. Okay, now we have the cyclic subgroup generated by 4. Now, all the numbers in this subgroup are also in the subgroup generated by 2. So I want to draw a line connecting 4 to 2, indicating that the cyclic subgroup generated by 4 is a subgroup of the cyclic subgroup generated by 2. Next we have 6. Let's see here, where does 6 go? Further down, because it's even smaller. But maybe notice this time that 6, all the multiples of 6 will appear in both the cyclic subgroup generated by 2 and 3. All the multiples of 6 are in both of them. So I want to draw a line connecting this subgroup to both of these two cyclic subgroups, okay? Because the cyclic subgroup generated by 6 is a subgroup of both of these two. We have the cyclic subgroup generated by 9 next, which is of order 4. All multiples of 9 are multiples of 3, so I want to connect from 9 to 3, because all of these numbers appear up here. The cyclic subgroup generated by 12, okay. Now, 12 is a multiple of 6 and a multiple of 4. So all of the multiples of 12 over here will appear in the multiples of 6 as well as the multiples of 4. So therefore, the cyclic subgroup generated by 12 is a direct subgroup, if you will, of the subgroups generated by 6 and 4. The cyclic subgroup generated by 18 consists of 0 and 18. It's a subgroup of these two, because 0 and 18 appear both in the cyclic subgroup generated by 6 as well as by 9. And then finally, the trivial subgroup at the end. It's of course a subgroup of both of these guys, so I'll connect them like that, okay? And that's what the subgroup diagram for Z36 would look like. I'm not sure if you guys really needed that, but maybe it's good to see, because you'll probably do it later at some point. And I guess that's all that I have to say. This video is kind of long at this point, so I'll just wrap things up with that. Just kind of in summary, though, going back to what I started with. So anytime you have symmetries, you're going to have a group, okay? So studying abstract groups is kind of a way of studying symmetries in general. And that's the reason why groups are important, because lots of problems involve symmetry. Symmetry makes problems easier when it's present. So a study of symmetry is very useful, and the study of symmetry is sort of subsumed by the study of abstract groups. Okay?